Hello, everyone. Today, going to be looking at Section 8, Chapter 5, Section 8, Graphing and Solving Quadratic Inequalities. And we're going to be looking at two different types today. The first type will be two variable inequalities that have y's and x's. And the second one will have just x's, single variable inequalities. So if you're looking at what's on the screen right now, I'm hoping you recognize a lot of it. There are three steps to graphing quadratic inequalities. Step one is one that we've already seen in this chapter. We're going to graph the parabola as we learned in 5.1 and we reinforced in 5.2. So we're going to find the axis of symmetry, find the vertex, make a table, we're going to graph the parabola. Step two, solid or dashed parabola. Again, just like before, this has to do with what kind of sign is here. If it's a strictly less than or strictly greater than, it'll be dashed. If it's a less than or equal or greater than or equal, it'll be solid. And then finally, where do we shade? In this case, on this problem, it's shaded below the parabola because it was y is less than. If it was greater than, we'd shade above or inside this parabola. So when it comes down to it, all three of these steps are things that we've seen before. Graphing parabolas early in this chapter, and then solid dashed line, where to shade above, below, multiple times already in this course, chapter 1, chapter 2, chapter 3. So this should be a lot of familiar knowledge when it comes to two variable inequalities. So we're going to do an example right now, just to reinforce and remind you of how do we graph a parabola. So I've got y is greater than 2x squared plus 8x plus 5. Two variable inequality, got y's and x's. Y's by itself. So let's get started. Step one, we're going to find the axis of symmetry, which is always, if you remember, at x equals negative b over 2a. So in this problem, because a is 2, b is 8, c is 5, that will be at x equals negative 8 over 2 times 2, or negative 8 over 4, x equals negative 2. That is going to be my axis of symmetry on this problem. So grab my ruler, dashed line there at x equals negative 2. That leads us into our vertex. The vertex has to be on the axis of symmetry, so we know that the x coordinate is negative 2. And I'm going to use that information, plug in negative 2 into the polynomial above to find my y coordinate. 2 times negative 2 squared plus 8 times negative 2 plus 5. Which order of operations? I'll do the power first, the exponent. So 2 times 4 minus 16 plus 5. 8 minus 16 is negative 8 plus 5 would give us negative 3. So vertex, negative 2, comma, negative 3. Now I'm going to take that and make that the basis of my table, the very center. Because again, we know our parabolas are symmetrical. So if I know negative 2, negative 3 is on this parabola, then I'll just go negative 1, 0, negative 3, negative 4, a couple points on either side of the vertex and start plugging in. I might plug 0 in first because I love plugging in 0. 2 times 0 squared plus 8 times 0 plus 5. That's just going to be 5. 1, 2, 3, 4, 5. So 0, 5 is a point on this parabola. And because it's symmetrical, I know that negative 4, 5 is also on the parabola. So 2 away from the axis on the right, 2 away from the axis on the left. That's what we get. What about negative 1? 2 times negative 1 squared plus 8 times negative 1 plus 5 will be 2 times 1. So that's 2. Minus 8 is negative 6 plus 5, negative 1. So negative 1, negative 1. Negative 3, negative 1. And we can see our parabola. Kind of steep, opening upwards, makes sense with what we know. So let's ask ourselves, solid or dashed parabola? It is strictly greater than, so it will be a dashed parabola. And we'll just freehand it in as best we can. Y is greater than. So my tip for you, because like when it comes to parabolas, is greater than inside, outside. How do we know? I always just go to my y-intercept, not my y-intercept, excuse me, go to my vertex and say y is greater than. I want to shade the region above my vertex. So this region, which shows me, okay, that's the inside region. And there is that two variable quadratic inequality. So little review of how to graph a parabola. We graph it, axis of symmetry, vertex table, and then solid or dashed, and where do we shade? So that'll be our example for two variable inequalities. But we do want to talk about one variable inequalities. So there are a couple different ways to do this. And the way that I'm going to propose is a little different from the textbook. So the textbook talks about one variable, put it on a number line, because we only have, if it's a two variable inequality, we have x's and y's. But if it's a one variable inequality, it's just x's on a number line. That will absolutely work. But what I'm going to do is kind of demonstrate how to adapt this onto the more familiar coordinate plane. So here's what I'm going to do. I'm going to take this quadratic expression on the left, and I'm going to plug it into my calculator. So in my calculator, I'm going to say x squared plus 8x plus 7, and I'm going to graph. And if I need to, if my window looks a little funky, I'll set it back to my familiar -10 to 10 in both directions. And that's what my graph looks like. So when this inequality says, where is the graph less than or equal to 0? What that is saying is, where is the graph below the x-axis? Less than or equal to 0 means negative. So where is it below the x-axis? So just looking at this graph, and I can use the trace function, I can say, okay, it looks like -1, it hits at -1. And then where is the other one it hits? I'm counting 2, 3, 4, 5, 6. It looks like -7, so I'll trace -7. Yep, sure enough, -7. And all I need is the bare bones sketch, the most bare bones sketch, knowing the roots. So I know that it looks something like that. So the question is, where is this parabola negative? Where is it less than or equal to 0? And well, just from observation, we can see it's less than or equal to 0 at all these points below the x-axis. So what does that mean for my solution? It looks like anything in between -7 and -1. So I can just say -7 is less than or equal to x is less than or equal to -1. Any x value in that range will be below the x-axis, will be less than or equal to 0. If you like interval notation, we can always write -7 to -1. Same answer, just written a little differently. So this is really, I think, the simplest way to visualize one variable inequalities. Look at the graph, find the roots, and then we're just asked, where is it less than or equal to 0? So where is it below the x-axis? And we can just see that from observation. Let's try one more. So 3x squared minus 7x minus 1 greater than 0. Again, I just need the most basic idea of what this graph looks like and what the roots are. So I'm going to come back to my calculator. I'm going to say 3x squared minus 7x minus 1 graph. Opens upward, kind of steep. But where are the roots? It looks like maybe 0. No, 0 is -1. So that's not a root. It's not hitting the x-axis. So like -0.5 maybe. And that's way too high. So how do we find the roots if they're not nice numbers? Again, our calculator can really help us out with this. I'm going to go to the calc menu, second calc, and I'm going to ask it to calculate the 0. It will ask me those 3 questions. It will ask me for a left boundary. So anywhere to the left of that 0. Anywhere to the right of that 0. So I'm going to use the arrows to move it a little bit to the right. It asks me to guess, so I'll get it kind of close and hit enter. And negative 0.1350. So just barely negative. Negative 0.1350 apparently is a root. Probably wouldn't have figured that out just by looking at it, by guessing, but that's where the calculator comes in handy. Let's find the other root. So I'll say calculate the other 0. And it will know to do the other 0 because I'm going to move the cursor just to the left, just to the right, get it close enough to guess, 2.4684. So 2.4684, we'll call it right there, 2.4684 is the other root, and it opens upwards. So it goes something like this. We don't care how far down it goes, really, how steep it is, because all we are caring about in this problem, one variable inequality, is where is it greater than 0? You look at this graph and you say, well, greater than 0, anywhere that it's above the x-axis, so anywhere here, that's what I want to include in my answer. So where is that in terms of my x values? That left-hand one, I'm going to say, well, anything less than negative 0.1350, because anything less than that in the x direction will be to the left, and that's my yellow shaded region. What is this? This is anything greater than 2.4684. So combined, what is my solution? What x values make this a true inequality? X is less than negative 0.1350, or x is greater than 2.4684. Looking at just on the graph, where are we above the axis? Because we're looking for greater than. If you want to write it in interval notation, we can use the union operator to combine a couple sets. So I might say negative infinity to negative 0.1350 joined with 2.4684 to infinity. Again, 2 different ways to write the exact same thing. So one variable inequalities throw people off a lot, but really all it is pretend it's a 2 variable, graph it, and then answer what it's asking. For that top one, where is it less than or equal to 0? Anywhere below the x-axis, so between -7 and -1. For the second one, where is it greater than 0? Anywhere above the x-axis. So in this case, less than negative 0.1350 or greater than x equals 2.4684. So this is all there is to quadratic inequalities, these one variables, as well as if there are 2 variables, a y and an x, solid versus dashed, shade above, shade below, and we already know how to shade a parabola. So hopefully this helps as you are looking at 5.8. If you have questions, please be sure to reach out. But otherwise, I will see you next time.